Ladies and gentlemen, this is going to be a long one, so strap yourself in and prepare for a methodical and thorough debunking of one Jeffrey P. Tomkins from the Institute for Creation Research. Now, for about the past decade or so, he's been trying to downplay the percentage DNA similarity between chimpanzees and humans. In his mind, if the number is much lower than the 96% to 99% given by secular researchers, then chimpanzees can't be related to humans, evolution must be false, and God must have created everything in 6 literal days. So to that end, he has published this paper way back in 2016. Apologies, it took me more than 7 years to address it properly, but funnily enough, when it was published, I'd just gotten out of hospital after nearly dying from leukemia. Anyway, what he did was download an enormous amount of raw DNA sequence of the chimpanzee and then compared those sequences to the human genome using software called BLAST. Once he tallied all those results, he came up with an overall percentage identity of 85%, which is obviously much lower than the secular numbers. And basically his thesis is that there is a substantial amount of accidental contamination in the earlier data sets, and those data sets were used to construct the chimpanzee genome, while the later sets were less contaminated, and that's where he's taking the 85% from. And just a little bit of foreshadowing, that line that I've highlighted and underlined will be important later. So just to address some of the points he makes in the abstract, yes, the chimpanzee genome available at the time, called Pantro4, did use the human genome as a scaffold. And at a very simplistic level, what this means is this short sequence of chimpanzee DNA looks very similar to this sequence of human DNA, and that sequence of human DNA is found in the middle of human chromosome 6. So I'm going to assume that this short sequence of chimpanzee DNA also belongs in the middle of chimpanzee chromosome 6. This is very different to contamination, where a sequence of human DNA is accidentally included in the chimpanzee genome. So using the human genome as a scaffold does not mean there is human DNA in the chimpanzee genome. So again, Tomkins concludes that the early chimpanzee DNA sequencing that contributed to the first draft of the chimpanzee genome, which was published in 2005, he contends that it was contaminated with human DNA, while the later sets were less contaminated, and therefore the chimpanzee genome is approximately 85% identical overall to human. And this is the graph that shows you his overall thesis. On the x-axis, you've got these data sets in roughly chronological order, and on the y-axis, you've got the percentage similarity for each set when compared to the human genome. So his general idea is that this later stuff is less contaminated because reasons, and this earlier stuff must be contaminated because it's more similar to human than the later stuff. And that headline figure of 85% comes from this table in his paper. On the bottom 2 rows, you've got the data set split up into pre-2005 and post-2005, and the later ones are somehow, quote-unquote, less contaminated. And they are only 85% identical to human, according to Jeffy's numbers. So let's have a closer look at how he actually calculates that overall percentage identity, and I've highlighted the specific line in green. So nident stands for the number of identical nucleotides, and qlen is the length of your query. So the overall percentage identity is simply the number of nucleotides that match divided by the number of nucleotides that we were searching for. And here's a really simple example. The chimpanzee query sequence we've got is 10 DNA letters long, and we're looking in the human genome for the closest match, and we've found the sequence at the bottom, and 8 out of the 10 nucleotides match. So the overall identity is 8 out of 10, which is 80% identical. Very, very simple stuff. But let's try a real-world example. So this DNA sequence on screen is literally the first sequence in the first set of those 101 data sets. So certainly not chosen at random, but the point I'm going to illustrate here stands anyway. And we're going to use the BLAST program to try and search for this chimpanzee sequence inside the human genome. So it goes away and does that, and here is the output. So what are those numbers? Well, they correspond to the out format parameter that we specified at the top. So the first field is the query identifier, or the QSEC ID. Then QStart tells us where in the query sequence our alignment begins. Query end is obviously where that alignment ends. Nident is the number of matching nucleotides. Alignment length is the length of the whole matching sequence between human and chimpanzee. And QLen is the length of the query that we submitted. And using Tomkins' formula, the overall identity we get is 680 matching nucleotides over a query length of 737, which gives us 92.3%. So if you wanted to visualize this result, the purple bar is the chimpanzee query sequence, and the blue bar is the best match that BLAST could find in the human genome. And the thing to really take note of is that the first 53 letters of the query sequence didn't match. But for the remaining 684 letters, you'll see that 680 of them matched the human sequence. And that's over 99% identical. So what's the story with those first 53 letters? Why didn't they match at all, given that the rest of it was 99% identical? And the answer to that is hinted at in Jeff's paper. So in the materials and methods section, Jeff says, low quality bases were end trimmed using a Fred value of 20, vector sequence was trimmed using the comprehensive NCBI file, and empty sequences and those less than 100 bases were discarded using the Lucy software package. So there's a lot to unpack here. First of all, low quality bases were end trimmed. So the method used to sequence this DNA is called Sanger sequencing. And one of the disadvantages of Sanger sequencing is that after around 700 base pairs of each fragment, the ability to accurately determine the next DNA letter in the sequence decreases. So using a Fred value of 20. So a Fred value or a Fred score is a measure of the probability that a DNA letter has been correctly identified. And it's based on a log 10 scale. So a score of 40 means that there is a 1 in 10 to the power 4 chance that the letter is incorrect. A score of 30 means that there is a 1 in 10 to the power of 3 chance. A score of 20 means there is a 1 in 100 chance that it's wrong. And a score of 10 means that there is a 1 in 10 chance that it's wrong. The vector sequence was trimmed. Right, so part of the process of creating lots of copies of the DNA you want to sequence is packaging it up into what's called a vector. And that vector is then taken up by a host, such as E. coli, which then makes many, many copies. And the sequencing process generally reads a chunk of the vector's DNA in addition to the DNA that you are targeting, such as chimpanzee DNA. And I have to say that cloning vectors are fascinating. So that's Eric Lander on the screen there, and he is a great lecturer. And I recommend checking out these 3 videos in particular, but also check out the lecture he does on Sanger sequencing. Some of the little genius ideas that people have had to advance the science just blow me away. Anyway, highly recommend. So let's try that same sequence, but instead of searching the human genome, we're going to blast it against the chimpanzee genome. And if we run that command, we get very similar output. Just as before, the first 53 characters do not match. But for the remainder, instead of only getting 680 matching, we get the full 684 as a perfect match. So our overall identity as a percentage using Tomkins' calculation method is 92.8%. And that sounds like a big problem, because if we are comparing chimpanzee DNA to the chimpanzee genome, we should get a 100% match for the entire sequence. So obviously those first 53 DNA letters are leftovers from the cloning vector and do not belong to the chimpanzee genome, and therefore should not be part of the calculation for the overall identity. One way around this issue is to calculate the overall identity as a percentage of the length of the alignment, which was 684 base pairs, instead of as a percentage of the length of the query, which was 737 base pairs. This would give a result of 100% for comparing chimpanzee DNA to chimpanzee DNA, as it should be. For comparing the chimpanzee DNA to the human genome, 680 matches from an alignment 684 base pairs long would give a result of 99.4%. However, if you are using Tomkins' calculation method, so overall identity is the number of matched nucleotides divided by the number of nucleotides you searched, then you would want to be doubly sure that you have removed all of the vector sequence and all the low quality bases. Dun, dun, dun! So here's another excerpt from Jeff's paper. He says that after trimming the low quality bases and removing the vector contamination, he got an average query length of 704 bases. And the only way to check whether he has correctly trimmed these sequences is to download all 101 datasets and trim them myself. And after everything was downloaded and a bunch of additional files were created, it took up 358 gigabytes of disk space. So I'm not really surprised that no one has tried to replicate this study. Luckily, I'm the king when it comes to shell programming, so I had my machine do it all automatically. So we've discussed Tomkins' parameters a few minutes ago, and he said that low quality bases were n-trimmed using a Phred score of 20. Now I had a look at all the command line options for Lucy, and I couldn't find an option where you could provide a single Phred score. So most of the options involved some kind of sliding window of Phred scores. So honestly, I'm not too sure what to make of this. Maybe Jeff wasn't clear on his command line options. Maybe he used a different version of Lucy. Who knows? He did supply a file that could identify and remove specific vector sequences, but that file no longer exists on NCBI servers, so I simply use the defaults that came with Lucy. So we know Jeff got an average query length of 704 bases. What was my average query length? Once again, I'm the king of shell programming. By the way, you can see all the code and all the results of that code in my GitHub, which is linked at the bottom. And you'll see that my average query length was 676.4 bases and Jeff's was 704. And this is the big question. So remember that Jeffy T's calculation method took the number of identical nucleotides and divided it by the query length. But if his query includes DNA that is neither chimpanzee nor human DNA, then he will be understating the overall percentage identity. He'll be in that really awkward position where comparing chimpanzee DNA to itself will give you an overall identity substantially less than 100%. So this question, who trimmed correctly? Did I trim too much? Or did Tomkins not trim enough? So let's blast 1,000 of these trimmed sequences against the chimpanzee genome and see if the length of the alignment is still less than the length of the query. Note that I'm blasting against the most recent chimpanzee genome, which I personally have named Pantro7. So Pantro7 is not its official name. But if you have a look at the names of the chimpanzee genomes over the years, it blows my mind that they called the most recent one Pantro3. Anyway, why didn't Jeff run an experiment like this? To me, this is an incredibly obvious thing to do, and I'm, shall we say, quite suspicious that he didn't. So, once again, I'm the shell scripting king. All this one does is read the individual BLAST CSV files that were produced and counted up the number of identical nucleotides, the total alignment length, the total query length, and the number of results in the file, which is usually around 1,000, but there are some queries that did not find a hit. And here are the results for just a small handful of the data sets. And what we're looking at here is the average length column as a percentage of the average query length column. And in particular, we're looking at the rows for Pantro 7, which are the chimpanzee rows. And you'll see with my handy dandy yellow notation that especially in the later data sets, even with my shorter queries than Jeff, I'm still not getting 100% matches against the chimpanzee genome. So if these sequences have been trimmed quote unquote perfectly, then we would expect the average alignment length for the Pantro 7 hits to equal the average query length. So I blasted a total of 20,000 chimpanzee sequences against the chimpanzee genome, and the average length of those alignments was 664 base pairs. So the answer to the question of whether I trimmed too much or Tomkins didn't trim enough should be pretty obvious. If Tomkins' average query length is 704 base pairs, then he is already understating his result by more than 5 percentage points. And this is the first adverse finding for this paper. Dr. Tomkins has apparently not trimmed the raw sequences sufficiently, and combined with his calculation method of dividing the number of identical nucleotides by the number of nucleotides submitted to BLAST, he is understating his overall percentage identity by more than 5 percentage points. If Dr. Tomkins had done some more investigation into the results and/or implemented a sensible control, like blasting the same sequences against the chimpanzee genome, then this error would have been apparent upon examining the results. Okay, so the next thing we're going to look at is what Jeff likes to call non-hitters. Now, this big wall of numbers is the results from blasting 1,000 chimpanzee sequences against the human genome. And you can see in the left column, I've chosen every fifth set, so 5, 10, 15, 20, all the way up to 100. The next column is the number of identical nucleotides, which is just the number of matching DNA letters. Next column is the length of the alignment between the two, and then the query length. But the main column we're looking at in this section is the count. This is how many results we got back from BLAST out of the 1,000 sequences that we searched for. So you'll see for the first few sets, they all returned 1,000 queries, but in the later data sets, you'll see that number drop down to about 940. And if you look at set number 80 in particular, we only got 891 back. And if you look back at Jeff's graph, you'll see that's the basic pattern. The percentage identity starts out pretty high and then gradually falls off when you get to the later sets. And you'll also see that set number 80 being an outlier. So that all seems to check out. But, and here's the big problem. On screen now are the results for blasting so-called chimpanzee sequences against the chimpanzee genome. And we're seeing basically the same pattern as we did when we blasted them against the human genome. Nearly all queries returned a result early on, while the later sets get progressively worse. And remember that Jeff is counting any non-hitter as a 0% match against the human genome. But in these later sets, there are 5 to 6% of supposedly chimpanzee sequences that aren't even matching the chimpanzee genome. So once again, if Tomkins had run some decent controls, this problem would have been obvious. And we'll declare this adverse finding number 2 in a minute. But before we do that, we should actually figure out what the problem is with these non-hitting sequences. So on screen is some shell scripting magic, and all it does is compare the results that we got to the original query file and work out which sequences did not return results and stuck those in a separate query file. And as it turns out, there were 375 non-hitting sequences. And there's a cool function in the command line version of BLAST where instead of querying a database on your local machine, you can actually tell it to query the database on NCBI's servers. One thing I want you to notice though is that I've added an output parameter called stitle, And all S-title does is tell you the name of the organism that the query found a match against. Dun, dun, dun! And here are the results of that blast. So these are in random order, but if you look down the list, you'll see a whole bunch of expression vector, cloning vector, Clostridium difficile, E. coli, Bacillus amyloliquefaciens, vector, cloning vector, E. coli, etc., etc. So remember, these sequences are ones that Jeff assumed were valid chimpanzee sequences that he blasted against the human genome, got no result, and counted them at 0%. Bad Jeffy. Now, if you look at this list closely, right down the bottom, you'll see this one, pan troglodytes chromosome 2, and that is obviously the chimpanzee. But is this sequence actually a chimp sequence? No, it's not. I won't bore you with all the details, but all of the above sequences are also contaminated with vector sequence, and this is why BLAST finds a match within them. So finally, we get to adverse finding number 2. Those chimpanzee sequences that did not find a match in the human genome were counted as a 0% match between chimpanzees and humans. But on closer inspection, those non-hitters are actually cloning vector contamination and not chimpanzee sequence at all. So, just to recap, Jeff claimed that the earlier chimpanzee datasets were contaminated with human sequence, and that explained the higher percentage identity. This is demonstrably false. The earlier datasets were actually less contaminated, and the ironic thing is that the only contamination was from vector cloning sequences, not human contamination at all. If Jeff claims that there is human DNA contamination in these datasets, then there is an incredibly obvious question that he chose not to answer. Where is the list of sequences in these chimpanzee datasets that you believe are human DNA contamination? The fact that he didn't even try to identify them is pretty telling. So now that we've dispensed with Jeff's result, what is a reasonable estimate for the overall percentage identity given my results? So remember, Jeff's formula was the number of identical nucleotides divided by the total query length. But we saw that because he didn't trim the sequences properly, then we got a result less than 100% comparing chimpanzee sequences to the chimpanzee genome. So what I propose is the number of matching nucleotides divided by the total alignment length. And on the 20,000 sequences that I blasted, I got an overall percentage of 96.94%. And funnily enough, that's incredibly close to the result I got way back in 2014 when I challenged Jeff's original paper where he claimed a 70% identity between chimps and humans. The other possibility, which is a little more conservative, is that I could take the number of matching nucleotides and divide that by the total alignment length when I blasted those same sequences against the chimpanzee genome. That's a fairly crude control to account for the trimming problem, but when I do that, I get an overall identity of 95.87%. But the big question is, why does Jeff Tomkins continually get overall numbers much lower than this? He's published several papers on the topic, but each one of them has fatal flaws, and those flaws are different for each paper. And he's been told about these flaws over and over again, but refuses to correct for them. So I have absolutely no qualms about calling Jeff Tomkins dishonest. He is quite simply lying for Jesus.